Yes, my dear student, let us start the sequence topic. Today, I would like to give you the definition of the sequence, type of the sequence, and the boundedness, unboundedness, convergent sequences. Okay, let us start with the sequence. When I consider the sequence, it is nothing but a function. Let n be the set of natural number, x is a non-empty set. Then there exists a function s from n to x defined by s of n equal to an for all n in the set of natural number. Then this x is a sequence, a set of sequence or set of elements. The sequence has infinite number of terms, then it is called an infinite sequence. Suppose x equal to r, then set of real numbers, then it is a real sequence. If x equal to c, then it is a complex sequence. Then boundedness of the sequence. A sequence an is called bounded above if there exists a real number capital M such that an less than or equal to capital M for all n belongs to n. A sequence an is called bounded below if there exists a real number small m such that m is less than or equal to an for all n belongs to the capital N. That means in the sequence an, all elements are less than or equal to some natural number m. This m is called the upper bound of the sequence an. And similarly, if all elements of that sequence an are greater than or equal to small m, then the small m is called lower bound of the sequence. So based on this, I would like to define least upper bound of a sequence. Suppose a sequence has a least upper bound, that is u, if these two conditions are satisfied. So an is less than equal to u for all n. So all elements of the sequence are less than equal to u. And second condition is there exists an epsilon positive such that u minus epsilon is less than an for at least one element in the sequence. An is one element in the sequence such that that is greater than u minus some epsilon. Epsilon is a very small quantity. Then this u is called least upper bound or LUB. Similarly, greatest lower bound of a sequence. A real number small l is said to be a greatest lower bound of the sequence an if these two conditions are satisfied. That l is less than or equal to an for all n. That means all elements of the sequence are greater than that l. And for given epsilon positive, there exists some natural number n such that l plus epsilon is greater than an. That means this at least one element in the sequence is smaller than l plus epsilon. Earlier all elements are greater. When you add some epsilon, that one element becomes smaller than that l plus epsilon. Then this l is called greatest lower bound of the sequence or GLB. So limit of a sequence. A point l is called limit point of a sequence an if there exists an epsilon positive such that an minus l less than epsilon for infinitely many n belongs to n. That means for different value of n, an minus l is less than epsilon, that l becomes a limit point of the sequence. So it is entirely different from the limit of a sequence. A number l is called limit of a sequence an if there exists epsilon such that an modulus of an minus l is less than epsilon for all n. For all n greater than n, if this condition holds good, then we say that l is limit of the sequence, or in other words, limit an as n tending to infinity is equal to l. Now, convergence of the sequence. A sequence an is said to be convergent if there exists an l which is limit of the sequence, which is finite, existent finite. That means a sequence an is said to be convergent if there exists a number L such that for a given epsilon positive there exists a natural number n such that an minus L is less than epsilon for all n greater than n. In other words, L is limit of the sequence, limit an as n tending to infinity equal to L, where L is a finite number. If L is infinite, then sequence is divergent. If the sequence neither convergent nor divergent is called oscillatory sequence. So these are the some examples for the convergence of the sequence. So these convergent and divergent of sequence. Here all elements are equal to 1 of the sequence, then this is a constant sequence and it converges to 1. Here that n, the sequence n, where the nth term is n, when I apply the limit as n tending to infinity, n becomes infinity, the limit does not exist, or in other words it is a infinity, then it is divergent. Similarly 1 upon n, when I apply a limit to when n tending to infinity it becomes 0, then its limit is 0 and it is a convergent sequence. And similarly n by n plus 1, so its limit is 1, therefore its limit is 1, which is finite and is convergent. So there is a first theorem of the sequence. Limit of a sequence is unique, or every sequence has a unique limit. So limit is always 1. Only one limit we have for each sequence. Suppose this is not possible. Let us start with the contradiction method. In the proof, let L1, L2 be two limit points of a sequence an such that, actually that I have forgotten, it is L1 minus L2 is greater than epsilon. So that means L1 not equal to L2. So the difference is some positive number is greater than. So let us start with A, as L1 is a limit of the sequence. So by definition of the limit, an minus L1 less than epsilon by 2 for all n greater than or equal to some n1. Similarly, L2 is also limit point, an minus L2 less than epsilon by 2 for all n greater than n2. So let us consider n is maximum of n1 and n2. So then let us consider L1 minus L2 is equal to modulus L1 minus an plus an minus L2. So add and subtract an, and by applying a modulus condition separate these two, and L1 minus an is less than epsilon by 2, an minus L2 is also less than epsilon by 2, which is epsilon. So this is contradiction, because I have taken that L1 minus L2 is greater than epsilon, but here I got L